Okay, so let's look at how this is called the Hodgkin-Huxley equations, which is we're going to look to see that it's a set of ordinary differential equations, and we're going to calculate what dv dt is, and dv dt, if we remember, dv dt is equal to I. So this is one of those sort of basic current laws, and so this is the membrane capacitance. And this is the current inside the cell, across the membrane. This is the membrane current. And that membrane current can be broken down into each of these currents separately. And so what we'll do is we'll write this as equal to minus G sodium. So this is essentially equal to, this is what's called the conductance. Conductance, and that conductance is dependent on time and the voltage of the cell, of sodium conductance. So essentially we're representing this permeability thing here. And we multiply the conductance times, and I got to get the sign convention correctly, times the potential for that particular ion. So it tells us the voltage that we're at now to the reversal potential of that particular ion. So this is the potential of that particular ion. And the further this voltage is away from the sodium, the greater this current is. And the closer it is to this one, the smaller the current is, right? So this is the sodium conductance plus, and then we'll put in a potassium conductance, T comma V times V minus EK plus, and then there's a leak current, which tends to be a constant, V minus E leak. This E leak, usually we set to something like, I don't know, it's in the equations. It's one of those things I don't think about. Anybody know offhand? The E leak is around 0 millivolts, is that right? Minus somewhere, it's minus 20, minus 40 millivolts. Let's just say minus 20 millivolts. This one is minus 120. This one is positive 60. And we could change the sign here. Usually we bring this capacitance across. So we essentially write this as, we'll bring this across, if that's okay, 1 minus over Cm. Hope that's okay. We just brought that across. So now we have dv dt on the left-hand side. So let's look at these conductances. Yeah?
Why is your conductance voltage a small v and your voltage for is that significant?
No.
Or are they supposed to
Chalk it up to crappy handwriting. Yeah. Thanks. It's what? V is the potential difference between inside and outside the cell. Exactly. It's the potential of the cell. Usually we assume the outside is equal to 0. And so therefore we only write V, as just what's the membrane. And this is, might be at rest, this is sitting at minus 60 millivolts, right? When we start simulating an electric field produced by an electrode, and we'll calculate as what the potential is due to that electrode as a function of space, we will then put that potential actually into this equation where we'll calculate what the difference between inside and outside is, the outside changing as a function of the electric field from the electrode. So we'll explicitly put that in. So that's why I'm saying it's the inside versus the outside. Okay, so let's look at something like GNA. GNA as function of T and capital V. That has what are called two gating terms. Those gating terms tell you how quickly something opens and closes. And so actually the first thing is what's the maximum conductance of sodium. So it's just sort of how many, this is dependent on how many channels how many channels are in and how big those channels are. So the more channels, the higher the maximum conductance is. And the next two terms sort of tell you what percentage of those channels are on. And so those percentages we can write as M, which is an activation term. This is activation. And that activation term is time and voltage dependent. And H, which is also time and voltage dependent. This is the inactivation. So we look to see what the maximum is. We multiply it by the activation, and this is a value between 0 and 1, and the inactivation 0 and 1. And what we'll find is that this activation opens up quickly. It is a very fast thing as the cell depolarizes. And then slower, but later to come on is this one. This one starts off high and then drops to 0. And it's when the activation opens up, what we'll find this one actually is activation moves up like this, and then the inactivation, which was high, will drop like this. And so you'll have, this is activation, and this is inactivation, or M and H. And when you multiply those two together, you get a curve that looks like this. Right? And so when this is 0 times 1, it becomes 0. And it's really peaked when they're both sort of midway. Okay? So it turns out that there's, we'll talk about subunits, but these channels that you have that open and close, it turns out that I think there's 5 subunits in a sodium channel, and 3 of them are voltage dependent. And you need all 3 of them open for the sodium channel to open. And so it turns out those have to coordinate, and that gives you a cube term. So this M tells you the activation of each individual subunit within the channel, and you multiply them together to get you the activity of all the entire subunit. And then this one here is sort of represented as, I think I have a picture of it. We call it the ball and chain model. So you can see this is the sodium channel. Here, this is actually what the sodium channel looks like in a protein chain. Well, this is sort of the secondary, this is tertiary, and this is sort of what it looks like. And these different domains, some of them are voltage dependent. This domain right here actually is what creates the shape of the channel, which actually can distinguish, is so precise, it can distinguish between the shape of a potassium ion and a sodium ion. I mean, it's really incredible that it can do that. What happens is as the voltage changes, so here if we change the voltage in the cell, this is what's called a patch clamp recording. So this is a glass pipette going on and recording from a single protein channel. This is what was discovered back in about the 80s by Nair and Sackman, and they could see this channel actually open and then close again. And so the opening, we talk about the probability of the opening given the activation, and then the probability of closing is due to the inactivation. And here, recording from 3 different ones, or maybe the same one over several different steps, we can see it's sort of a probabilistic when it's going to open and then when it's going to reclose again. And those channels tend to, and so what happens is when the voltage is changed, you can sort of see there's this protein is voltage dependent and actually causes it to corkscrew up, and it changes as the voltage changes, especially because the voltage gradient across the membrane, we're talking 100 millivolts or 60 millivolts across just a few hundred angstroms. And that ends up being an incredibly high charge density across that. And so a very small change of maybe 10 millivolts brings us closer to threshold, can actually cause a protein to corkscrew up and actually change the conformation of this channel, which then lets sodium go through. And then shortly after it starts going through, this protein, sort of seeing that the channel is open, gets sucked up and then clogs up the channel, and that shuts it off. And this is called the ball and chain model. You get the corkscrew, which opens it, and then the ball that goes and shuts off the potassium channel. We'll see, okay, well, the potassium channel is different in that when it turns on, it just stays open. If you hold it at the same voltage, it just stays open. And so it has 4 subunits. and it also has these little corkscrews in it, but it does not have the ball. So the GK T comma V is equal to G max of the potassium times N T comma V. So this tells you the activation of the sodium channel. There's 4 channels that need to open, so that's raised to the 4th power. So that's the Hodgkin-Huxley equations.